Throughout this course, we've expressed real numbers, those numbers that correspond to points on a number line, as endless decimal expansions. Here in this lecture, we ask, is there another systematic method of expressing these real numbers? The answer is yes. There exists an entirely different approach, one that leads to expansions now known as continued fractions. Here we'll study an algorithm for writing real numbers as an intriguing, repeated fraction within fraction and explore its ancient history. This elegant theory, which was foreshadowed by the work of ancient Greek, Arab, and Indian mathematicians, really blossomed during the mathematical renaissance of the 16th century. By considering several illustrations, we'll come to see how this method of writing real numbers leads to new insights and reveals otherwise hidden structure within the real numbers. We'll then revisit the golden ratio and discover that, in some strange sense, it is the least irrational of all the irrational numbers, thus adding another layer to its mystery and prominence. Well, let's recall from our divisibility discussions in Lecture 10 our desire to find the greatest common factor of two natural numbers. Euclid, in his book Elements of Geometry, developed an algorithm that offered an explicit procedure for finding the greatest common factor. The basic method involves repeated applications of the division algorithm, highbrow language for long division, which states that for any given natural numbers a and b, there exists a unique quotient q and unique remainder r that satisfy a equals b times q plus the remainder r, and the remainder r is modest. It's greater than or equal to 0, but strictly smaller than b. The crucial feature for us here is that the remainder r is always smaller than b, the divisor. So let's remember that. Well, to illustrate the method, let's find the greatest common factor of 41 and 130. Now, these numbers are small enough that we can actually find their greatest common factor by simply factoring each number and seeing the factors they have in common. Well, we note that 41 is actually a prime number, so no factoring is involved. There it is. And if we take 130, we'd factor it as 2 times 5 times 13. It's 13 times 10. Thus, the largest factor they have in common is the invisible number 1. That is, the only natural number that evenly divides both of them is 1. So actually 1 was an invisible factor in each of those factorizations. 41 equals 1 times 41. And so therefore, 1 is the greatest common factor, and as we said in Lecture 10, we'd say 41 and 130 are relatively prime. They share no prime factors. Well, we'll now find the greatest common factor of 41 and 130 by applying the Euclidean algorithm in order to illustrate the method of finding the greatest common factor. And so we systematically long divide, and so we apply long division until we come upon a remainder of 0. So applying the Euclidean algorithm, what we see is 130 equals, well, in this case, it's 3 times 41 with the remainder of 7. So we see 130 equals 3 times 41 plus 7. And then, just like those late night talk shows where in fact, when new guests come out, the other guests slide down the couch. Well, we do the same thing here. We take the 41 and we slide it over, and we take the 7 and slide it over, and we ask 41 divided by 7 in some sense, and we apply the long division again, and we see 41 equals 5 times 7 plus a remainder of 6. Again, we slide everyone down, the 7 comes over and the 6 slides down, and we see that 7 equals 1 times 6 plus a remainder of 1. And then finally we slide down again, and we see that 6 equals 6 times 1 plus 0. So we see a remainder of 0, and that's the halting process, the halting process hits, we stop, and now what do? Well, the last non-zero remainder we see equals the greatest common factor. And if we move up to the previous line, we actually see 1 as the remainder, which is, of course, what we already found by simply factoring. Well, it'll be useful for the theory we're about to develop to remark that now that this process will always end in a finite number of steps, that we see that this process does terminate, since the remainders are always shrinking and are, of course, natural numbers until we finally reach 0. Well, we now follow the intellectual footsteps of our ancient Greek mathematical ancestors in an attempt to express the rational number 130 over 41. As a first step, we just rewrite the first 3 equations that we just found. And if we just divide the first equation by 41, we see 130 divided by 41 equals 3 plus 7 41ths. 41st, I guess I'd say. Take that next line and we divide through by 7, and we see 41 over 7 equals 5 plus 6 sevenths. And finally, in the last equation, if we divide through by 6, we'd see 7 sixths equals 1 plus 1 sixth. Well, we suddenly see some amazing structure. Ratios are appearing here on these equations, and also their reciprocals appear as well. For example, we see 7 over 41, and then later we see 41 over 7. 6 sevenths, and then we see 7 sixths. In fact, 7 over 41 equals 1 over 41 sevenths. In other words, that's a reciprocal of the other number. And 6 sevenths equals 1 over 7 sixths. This is an important little feature to realize, that if we look at 1 over 7 sixths and take the reciprocal, we get 6 sevenths. Well, using these reciprocal identities, we can substitute these equivalent values in for our equation, and we can deduce something interesting. So let's start off at the very top and see 130 divided by 41. Well, that equals, as we saw, 3 plus 7 over 41. But I can now write that as 3 plus 1 over 41 over 7. Well, now 41 over 7, we know what that equals. That equals 5 plus 6 sevenths. So I could write this as 3 plus 1 over 5 plus 6 sevenths. Well, now the 6 sevenths I could write as 1 over 7 sixths. In other words, I see 3 plus 1 over 5 plus 1 over 7 sixths. And 7 sixths equals 1 and a sixth. And so finally I see that 130 divided by 41 equals 3 plus 1 over 5 plus 1 over 1 plus 1 over 6. And thus we see we can write 130 over 41 as this nested fraction within a fraction. Well, this representation as a fraction within a fraction is called a continued fraction expansion. Now, as early as 200 BCE, Eratosthenes and others expressed ratios as continued fractions. Now, because we can perform the Euclidean algorithm with any 2 natural numbers, we see that we can write any ratio of natural numbers as a continued fraction of the generic form a0, so some initial number, plus 1 over a1 plus 1 over a2 plus 1 over a3 and so forth, down to the very last one, which would be 1 over a sub n, say, where all these a's are in fact natural numbers. Furthermore, since the Euclidean algorithm will always terminate in a finite number of steps, as we said before, because the remainders keep shrinking, then we see that all these continued fraction expansions must terminate as well. In other words, we only have finitely many a's in this nested continued fraction. In fact, upon closer inspection, we see that the a's are precisely the quotients we computed in our successive division Euclidean algorithm process. Similarly, it follows that any rational number whatsoever can be expressed as a finite continued fraction of the generic form a0 plus 1 over a1 plus 1 over a2 and so forth, down to a last one, say an, where now the very first number, a0, is allowed to be an integer because it might be negative if the original rational number were negative, while all the other a's remain natural numbers as before. It's also a straightforward task to show that any finite continued fraction must, in fact, equal a rational number. For example, the continued fraction 2 plus 1 over 4 plus 1 over 3 is, in fact, some rational number. And to find it, we just have to undo all that division. We'd say that this equals 2 plus 1 over, and then 4 plus a third is 13 thirds. So I see 2 plus 1 over 13 thirds. If I take the reciprocal of 13 thirds, I would see 3 thirteenths. And so I'd see the number is 2 plus 3 thirteenths, which is 29 thirteenths. And notice, indeed, that's a rational number. Thus, we have just shown that a number is a rational number if and only if it can be expressed as a finite continued fraction of the form a0 plus 1 over a1 plus 1 over a2 and so forth, with a last term 1 over an, where the a0 is some integer and all the rest are natural numbers. Well, this fraction within fraction notation, as you can see, a0 plus 1 over, a1 plus 1 over, quickly becomes very tiresome and cumbersome. Imagine textbooks having those long fractions in it. So we adopt some more compact notation. And we write a square bracket and then just list the a's, a0, a1, a2, all the way out to an, and close it up. And we understand that actually means those are the a's that go into the fraction a0 plus 1 over a1 plus 1 over a2 plus 1 over out to an. So, for example, we would write 140 over 13 as the bracket 3, 5, 1, 6. And that means the same thing. Those are the numbers we insert in our fraction. 29 over 13 would be written as 2, 4, 3, and so on. You get the idea. It is a compact way, but we always remember that those numbers are what go down that continued fraction. Now, given that the numbers appearing in the continued fraction expansion for a rational number are successive quotients found in the Euclidean algorithm, in some sense, the continued fraction expansion holds all the information from the Euclidean algorithm. It captures it all. Of course, the Euclidean algorithm requires that the two initial numbers be integers. And so the continued fraction expansion equals the quotient or ratio of these two integers. Furthermore, there's no way, of course, to apply the Euclidean algorithm with irrational numbers, and so we face an interesting question. Is there a way of finding a continued fraction expansion for an irrational number? Well, if we could find such an expansion for irrational numbers, then we would, in some sense, be able to extend some aspect of the Euclidean algorithm, a procedure just for integers, to the broader world of irrational numbers. Really exciting. Can this be done? Well, without any additional work, we can make one important observation. If an irrational number can be expressed as a continued fraction, then that continued fraction must never end. For we've shown that if a continued fraction terminates after finitely many steps, then in fact it must be a rational number. It must be a ratio. Hence, if a continued fraction expansion can be constructed for an irrational number, it must have an endless fraction within fraction structure. Well, this offers us a clue to how strange a creature this object might in fact look. Well, to discover how to uncover a continued fraction expansion for an irrational number, of course, we do what we always do. We revert back to something that we know how to do. So let's return to our previous example, 130 divided by 41, and wonder if we can find its continued fraction expansion without explicitly applying the Euclidean algorithm. Our hope is that perhaps we could extend such an alternative procedure to find the continued fraction expansions for irrational numbers. So let's see if we can fulfill our fantasy. So we'll view 130 over 41 now as a decimal. And if we take 130 and divide it by 41, we'd see 3.17073, 17073, and so forth. The 17073 repeats forever. We now remove the integer part and write the fractional part as 1 divided by the reciprocal of the fractional part. That's a little tongue twister, so let's write it out. We have 130 divided by 41 equals 3 plus the fractional part, 0.17073, and so on. Let's now write that as 3 plus 1 over the reciprocal, 1 over 0.17073, and so on. Well, now 1 over that small number is going to be a large number, so let's write it out. It's 3 plus 1 over 5.857, so on. Well, now let's pull out that 5. We're going to repeat the process. So pull out the 5, and I see 3 plus 1 over 5 plus 1 over 0.857, and so on. Well, the reciprocal of a small number like 0.8 something is going to be bigger than 1, and in fact, it works out to be 1.166, and so on. So I see that we have 3 plus 1 over 5 plus 1 over 1.1666, so on. Well, that equals 1 plus, that little 1.1666 equals 1 plus 1 over 0.16666, and 1 over 0.16666 equals a sixth. And so what we see is the original number equals 3 plus 1 over 5 plus 1 over 1 plus 1 over 6. And look, just as if it were magic, we just discovered the continued fraction expansion we found earlier. However, this time, we never used the Euclidean algorithm, only the decimal expansion for 130 divided by 41. Well, we'll now extend the previous process to generate continued fraction expansions for irrational numbers. The basic strategy is to first remove the integer part of the number and then consider 1 divided by the reciprocal of the fractional part. That's the trick. That's the secret. We write 1 divided by the reciprocal of the fractional part, and then we just repeat the process again and again. Rip off the integer part we see, then write 1 over the reciprocal of the fractional part, and keep continuing. This method will generate a continued fraction for any real number, rational or irrational. So, our method to find the continued fraction for any decimal number using a calculator is to first record the integer part of the number, and we'll call it A0, and then subtract that part, so we're left with the fractional part, and then take the reciprocal of the fractional part and remove its integer part, call it A1, and then we continue this process to generate all the terms in the continued fraction expansion. Well, let's compute the first number that we proved was in fact irrational long ago in our class, the square root of 2. Well, we write the decimal expansion of the square root of 2 as 1.414213 and so on. And so we rip off the integer part, 1 plus the fractional part, 0.414, so on, and then write the fractional part as 1 over the reciprocal, which is 1 over 2.414, and so on. And so what I see here is that the square root of 2 equals 1 plus 1 over 2 plus 0.414213, and so on. Well, at this point, we notice something truly amazing in those decimal digits, and something genuinely surprising, unexpected. We see a repetition in the fractional parts. Thus, when we take a reciprocal again, we'll see again the integer part equaling 2, and those numbers will repeat. Thus, just as we saw with decimal expansions of rational numbers, we see that the continued fraction for the irrational number square root of 2 is periodic. It equals 1 plus 1 over 2 plus 1 over 2 plus 1 over 2, and so forth forever. If we now turn to the second number we established was irrational, log of 2, then using a calculator and the procedure we just outlined, we'd see that the log of 2, if we look at its decimal expansion, equals 0.30102, and so forth. Well, we just now repeat the process. We pull off the integer part, which in this case is 0. So we have 0 plus 0.30 stuff. We write it as 1 over the reciprocal, which would be 1 over 3.32 stuff. Pull off the 3, and then have 3 plus the fractional part, 0.32 stuff. Write that as 1 over 3.106 stuff. Rip off that 3, take what's left over and write it as 1 over 9.4, and so on. And the process continues. And if we continue in this manner, finding the continued fraction expansion for log 2, we see that the log 2 continued fraction expansion begins 0, then a 3, then a 3, then a 9, then a 2, then a 2, then a 4, then a 6, then a 2, then a 1, a 3, a 1, an 18, and it goes on and so forth. So what we see is 0 plus 1 over, 3 plus 1 over, 3 plus 1 over, 9 plus, and so on down the line. Now, notice that there's no obvious pattern to the natural numbers appearing in the continued fractions that we see here, in this particular one. Now, those natural numbers that appear, those A's as we're calling them, are called partial quotients because they're part of the quotient that we're seeing here. Whether or not they form a pattern or not. Well, let's now note that in the case of each of these irrational numbers, as we've seen, we see that the continued fraction expansion is indeed endless, as we predicted. And so that at least we see that there's no signs of any of these things ending. Of course, with the square root of 2, we see that it's purely periodic after that first one. So, we've shown that a number is a rational number if and only if its continued fraction terminates in finitely many steps. In other words, there are only finitely many partial quotients, finitely many of these A's. In view of this fact and the continued fraction algorithm we found for general decimal numbers, we see that irrational numbers have unending continued fraction expansions. In fact, we see that a real number is an irrational number if and only if its continued fraction expansion is unending. Thus, we come upon a new definition of irrationality, one that is equivalent to the standard one, but nonetheless having a very different quality. So, the theory of continued fractions allows us to look at the notion of irrationality in an entirely new light. Well, let's take a moment to revisit some other famous numbers that we've already looked at and now consider their continued fraction expansions. If we compute the continued fraction for pi, then we would see, of course, the decimal is 3.1415 and so on. We pull off the 3 and then take the fractional part and write it as 1 over 7.06 something, and therefore we have a 7 plus a tiny fractional part, 0.06 something, which is 1 over 15.9 something. And if we continue this process, we develop the continued fraction for pi, which begins 3 plus 1 over, 7 plus 1 over, 15 plus 1 over, 1 plus 1 over, 292 plus 1 over, 1 plus 1 over, 1 plus 1 over, 1 plus 1 over, and it goes on and so forth. Again, there appears to be no obvious pattern to the partial quotients. Excuse me. I get choked up when I think about continued fractions. So while there's no particular pattern that we see, but we will say a little bit more about this in the next lecture, so stay tuned. Well, the theory of continued fractions was actually used by Ferdinand von Lindemann in 1882 to prove that pi is, in fact, transcendental. So this representation, while somewhat cryptic and not completely understood, remains an important and powerful number theoretic tool. If we just focus on the first two terms in the continued fraction expansion for pi, and ignore the tail, ignore the rest, then we notice that we see 3 plus 1 over 7, which equals 22 over 7. The familiar rational approximation we found for pi from our school days and also from the previous lecture in looking at Dirichlet's theorem. And we'll expand on this observation in the next lecture as well. The continued fraction expansion for pi appeared to have no easy-to-identify pattern. Let's now consider the continued fraction expansion for e, Euler's number, a number that, of course, is filled with surprises. If we begin with its decimal expansion, which is a 2.71828 and so on, then we'd find that it actually equals a continued fraction of the form 2 plus 1 over 1 plus 1 over 2 plus 1 over 1 plus 1 over 1 plus 1 over 4 plus 1 over 1 plus 1 over 1 plus 1 over 6 plus 1 over 1 plus 1 over 1 plus 1 over 8, and so on. And we see the pattern 2, 1, 2, 1, 1, 4, 1, 1, 6, 1, 1, 8, 1, 1, 10, 1, 1, 12. In fact, it's a difficult theorem, but a theorem nonetheless, that this pattern continues forever. We always see 1, 1 and the next even natural number. Absolutely spectacular. Well, this incredible structure hidden within the number e only comes into focus through its continued fraction expansion. Truly marvelous. Given this predictable progression, we see that the continued fraction expansion for e must be endless, and hence we see that e must indeed be irrational. Again, we see that we gain deeper insights into the structure of numbers by exploring their continued fractions. Well, I want to close this introduction to continued fractions by taking another look at irrationality. We've already seen that numbers come in two basic flavors, if you will. They're either ratios, namely rational numbers, or they're not, and we call them irrational numbers. A number is either one or the other. Just as the blessed event of a woman being with child. A woman is either pregnant or not. However, while it's nonsensical to declare that a woman is a little bit pregnant, we're now about to see that we can speak of an irrational number in some rough sense as being more or less irrational. Unlike pregnancy, here there are in fact degrees of irrationality. To develop this important refinement of irrationality, let's recall that we've proven that if a real number has a finite continued fraction expansion, then it's a rational number, and otherwise it's irrational. I now want to relate the partial quotients, the a's, appearing in the continued fraction for a number, say alpha, to the rational approximations for alpha that we considered in lecture 21. In some sense, which we'll make a little bit more precise in the next lecture, large partial quotients in a continued fraction for a number alpha give rise to rational approximations to alpha that are extremely close to alpha relative to the size of the denominators of the rational approximates. In some sense, they're inexpensive rationals really nearby alpha. Recalling from lecture 20 that the rational numbers themselves have no good rational approximations with relatively small denominators, we see that in some informal sense, an endless continued fraction, the larger the partial quotients, the more irrational the number is. And the smaller the partial quotients, the less irrational the number is. Liouville's number, that number we studied in lecture 20, that's transcendental because it has such amazing rational approximations by rationals having relatively small denominators. And so therefore, Liouville's number must have some incredibly enormous partial quotients in its continued fraction expansion, which it does if you look out far enough. Well, as we've also seen in lecture 20, transcendental numbers are, in some ways, as far from being rational as possible. So what would be the least irrational number? Well, since it must be irrational, we know that its continued fraction expansion must never end. And we also have claimed that the smaller the partial quotients are, the less irrational the original number is. Well, the smallest partial quotient possible would be the smallest natural number, which of course we all know is the number 1. Thus, in some informal sense, the least irrational number has a continued fraction expansion equal to 1 plus 1 over 1 plus 1 over 1 plus 1 over 1, and so forth forever, endlessly. But this is an expansion we've discovered long before we developed the general theory of continued fractions. We came upon this number in Lecture 6. There we proved that this continued fraction equals the golden ratio, 1 plus square root of 5, all divided by 2. So the famous golden ratio is, in some sense, the least irrational number, another title it can possess with pride. Well, let's now close this lecture by foreshadowing the ideas to be considered in the next lecture. What if we were to truncate the continued fraction expansion for the golden ratio? Then we would have a continued fraction expansion that is finite in length, consisting only of 1s, 1 plus 1 over 1 plus 1 over 1, and then it would stop. Well, since these continued fraction expansions are finite, then they must be rational numbers. And what are they? Well, just 1 alone is 1 over 1. 1 plus 1 over 1 is 2. 1 plus 1 over 1 plus 1 over 1 works out to be 3 halves. Then we would see 5 thirds. Then we would see 8 fifths. And look what's happening. We're uncovering ratios of consecutive Fibonacci numbers. In fact, we proved this observation for ourselves back in Lecture 6. And now we can celebrate this wonderful discovery within the broader context of the theory of continued fractions.